Kinetic molecular theory. This is a general theory developed to explain the behavior and theory of gases based on the motion of the particles. And the assumptions of kinetic molecular theory are that A, gases consist of tiny particles. In ideal gas theory, you assume that gases are actually points in space, and that they don't, even the particles, they take up no volume whatsoever, which is not true. Gas particles are real atoms and molecules, and they do take up space. Another assumption of kinetic molecular theory is that the distance between particles is large when compared to the particle size. The volume occupied by a gas is mostly empty space. And you can see why that would be true, because again, we take 18 milliliters of liquid water, and when that turns into a gas that has TP, it takes up 22.4 liters. And so the molecules take up 1,000 times more space as a gas, so most of that space is actually empty space. And 3, gas particles have no attraction for one another. And again, that's not totally true. They do, it's just really weak, which will become exacerbated at very low temperatures, as we'll see in a minute. Gas particles move linearly in all directions, frequently colliding with the container walls or other particles. Gas collisions are perfectly elastic. No energy whatsoever is lost during collisions. And that the average kinetic energy for gases is the same for all gases if it's at the same temperature. And that's important, because the kinetic energy of a gas is 1/2 times mass times velocity squared of the particles. And so if all gases have the same kinetic energy at the same temperature, 1/2 mv squared of gas 1 will equal 1/2 mv squared of gas 2. And if that is true, then if two gases are at the same temperature, they have the same kinetic energy. If a gas is lighter, it has to move faster to have the same kinetic energy. So the lighter a gas is, the faster it moves. The heavier a gas is, the slower it moves. But if two gases are at the same temperature, they have the same kinetic energy. 1/2 times mass times velocity squared for their particles is the same. And so if mass goes up, velocity's got to go down to compensate. If mass goes down, velocity's got to go up to compensate to maintain that constant kinetic energy at that temperature. Gases which behave under these assumptions are known as ideal gases. However, real gases are not ideal, because real gases are not points in space. They actually take up volume, which at normal pressures is negligible and can be rounded down. So like if the gas particles themselves are taking up 1,000th of the space, that's 0.1%, that can be ignored. But at very high pressures, the gas particles themselves may be taking up 30 to 40% of the space, and that's no longer negligible, and that cannot be ignored. And so that a gas will deviate from ideal gas law then. And at very low temperatures, as temperature goes down, as we saw, kinetic energy goes down. If kinetic energy goes down, you cannot change the mass of the gas, so that means velocity's got to change. Velocity goes down. As temperature goes down, velocity goes down. And so at extremely low temperatures, gases are moving very slowly, and now their intermolecular forces become important. Their intermolecular forces become substantial enough where they can stick to each other. And therefore, at high pressures and low temperatures, a gas can liquefy, which does not happen to theoretical ideal gases, but does happen to real gases, because again, real gases do take up space with their molecules because they're real atoms and molecules, and real gases do have actual intermolecular forces in between each other. Just at normal temperatures, they're negligible, and so they can be not counted, but at very low temperatures, they become extremely substantial. Dalton realized that if you have a mixture of gases, each gas in the mixture behaves as if it's the only thing in there. And so the total pressure of a gas mixture can just be found by adding up the partial pressures of each individual gas found in the gas mixture. And so we apply this when we collect gases over water. We have to take into account the fact that there's both the gas we're collecting and also water vapor, because you're over water. And so when you collect over water, you need to subtract the water vapor. The internal pressure in this bottle will be equal to the external atmospheric pressure. Otherwise, it would move the liquid to equilibrate that. And so the external atmospheric pressure will be equal to the gas you're collecting in your bottle plus the vapor pressure of water. So a sample of oxygen gas is collected over water at 22 degrees Celsius and 662 torr. What is the partial pressure of the oxygen gas? Well, if we look up the vapor pressure of water, which is just something that you look up, you'll see that it's 19.8 torr at 22 degrees Celsius. Therefore, the atmospheric pressure outside will be equal to the pressure of oxygen plus water vapor inside the bottle. So to solve for PO2, we subtract the partial pressure of water vapor from each side. And we see that of that 662 torr, 642 torr were due from the oxygen itself, and 20 torr was due to the water vapor collected also.